Hi everyone, this is Sean, um, and this will be the first part of a multi-part series of presentations I'll be doing on probability. And this in particular is on combinatorics, which is kind of a foundation of probability, one of them. So as you can see, I placed my probability uh, in the math section in the formal science. So it's formal science to the list of formal sciences. And because probability theory is pretty interdisciplinary within studies of math, I linked it to both focuses of math within math itself and also statistics, as you can see here. So getting to a quick definition of probability theory. It's the branch of math that's concerned with the likelihood of an event occurring or the likelihood that an event is true. Um, so before we jump into everything, I'll have a quick look at references here. So I used Wikipedia a little bit, but the main reference I'm using is this one. Probability for the Enthusiastic Beginner by David Morin, who's a Harvard professor. Really good book. Highly recommend it. So the topic, again, like I said, that we're covering in probability theory will be on combinatorics. And just as a note, all future topics that I'll cover will be added to this and branched outwards as child notes. But the focus of this presentation is on combinatorics. Combinatorics is defined as the study of how to count the various combinations, permutations, subgroups, etc., that can be formed from a given set of objects, people, etc. And like I said before, knowledge of combinatorics is vital for an understanding of probability, because when you're calculating the probability of an event, you have to know the number of potential ways an event can occur, which I'm sure we'll get into next chapter or next presentation, which will be on probability, generally speaking. So a major topic within combinatorics, I know that combinatorics is a like field of math. It's a whole subject area. So I didn't want to just assume that the stuff I was covering was all there is. So I added major topics in combinatorics just so that future contributors will be able to add other topics if they feel the need to. But what I added was about permutations, which as a note includes, which as a note includes permutations and combinations, but we'll get to that here. So just more defining terms, a permutation is a way of ordering a set of objects or rearranging an already ordered set of objects. And there's two kind of major things that, in my opinion, you need to know before starting to work with them based on what I've read. And first is the ordering and replacement of objects. And second is permutation of n objects themselves. And we'll start with this. So the permutations of n objects is like the simplest way you can calculate a permutation. So if you're just given a set of n objects, n factorial is defined to be the product of the first n integers. So the number of different permutations of n objects is n factorial. And I do say as kind of a footnote here that in the scenario, the number of objects in the set n is equivalent to the number of trials of n you have, but we'll get to that later in a little bit more detail. Factorials, for anyone who isn't familiar with it, are quantities calculated by, again, taking the product of the first n integers of an integer n. And this is the chart provided in the book that just shows factorials for the first like 6 numbers. So like if you look at 6, the first in, so if in is 6, the first in integers multiplied are 6, 5, 4, 3, 2, and 1, which equals 720. So once again, if you're trying to find the number of potential permutations of n objects, if you take the factorial of n, of the amount of objects, you'll get the number of potential ways that they could be combined. So now let's talk about ordering and replacement. So permutations can manifest, I guess, in like 4 different ways. As you can see here, they can either be ordered or unordered, and they can either be repetitions allowed or repetitions not allowed. So what I mean by repetitions allowed is it just means the same thing as identical trials. So examples of this include rolling dice, flipping coins, and drawing balls from a box with replacement. So essentially the idea is when you roll a dice, you can't remove one of the sides of the dice after you roll it. So then in your next trial, the next roll of the dice, you replace the item that's rolled instead of removing it. And unordered versus ordered. Oh, excuse me. Yeah. So, and then unordered without replacement means the same thing as depleting trials, or trials where the number of possible outcomes decreases by 1 after each trial, which is what a permutation is. As you'll notice, if you take each of these events as trials, you start with 6 and then you deplete the trial by 1 each time going down. And examples of this include picking committees of people because people can't be repeated, assigning people to seats, and drawing balls from a box and not replacing the balls after you draw them. So as far as ordered versus disordered sets, ordered sets are viewed as if they're in a line, whereas unordered sets can just be viewed as like an amorphous blob of items in a set or objects in a set. So an example of an ordered committee is one where all the members have given roles like president or vice president, whereas sticking to the committee example, an unordered committee is one where all the roles are equal. There's no hierarchy or system in place to differentiate your objects or your people in this case. So right, it turns out that whether or not your sets are ordered or unordered and whether or not repetitions are allowed or not allowed will actually affect the amount of potential events that can occur within that set. So we'll cover all 4 of these things here and the formulas associated with them. And this is just a couple of tables that kind of explain that there are, as you can see, there's 2 squared or 4 potential options for these. So there's order matters and with replacement. Here's an example. This is the example one down here, actually. And then this is like kind of a conceptual orientation to it. So from there, we can look at the 4 different, just zoom out here a little bit. We can look at the 4 different kind of conditions of ordering and replacement that exist within permutations. So looking at the first one up here, ordered sets, repetitions allowed. If there are n possible results each time a trial occurs, then the total number of possible outcomes where the order of the objects matters is n to the nth power. And examples of this situation would include rolling an n-sided die in times, or drawing one of big N balls from a box little n times and returning to the box each time so that the draws are equivalent. Yeah, that's probably the most straightforward. And you'll notice the biggest difference between this here and this here is that it's assumed in this example that big N and little n are equal. So you have the same amount of objects as you do trials. Whereas in this case, and this is permuted, so the trials decrease by 1, whereas this repetitions are allowed, so things aren't permuted, and there's potential space for big N and little n not to be equal, if that makes sense. Whereas if we look at this example, this is actually probably the closest equivalent scenario to this, because essentially this formula allows for big N and little n, the amount of objects you have and the amount of trials you have, to be different from one another. Whereas in this example, the amount of objects you have and the amount of trials you have to be the same in order for you to just be able to use the factorial formula. But you do derive this formula down here for ordered sets, repetition is not allowed, from this formula up here. As you can kind of see, all you're doing is you're taking that factorial formula and you're dividing it by the total number of objects minus the number of trials, and the factorial of that result. And that just accounts for, again, the differences between big N and little n. So yeah, then with unordered sets, it gets a little bit more complicated. I actually just wrote out this example because I thought it was a little bit clearer than the way it was listed out in the book. But both this example and this example use binomial coefficients, which are the coefficient of the n to the nth power term in the binomial expansion of x plus 1 to the nth power. So they're widely used in combinatorics and probability, and just in algebra, but they're expressed with this formula right here. And this here, n and k, is a way to express binomial coefficients. And when you're calculating both of these things, you're actually calculating this, which is what you're going to end up putting into the formula to figure out what your binomial coefficient is. So that's a little bit confusing, especially considering that the terms are alike in these examples, and in these examples that involve binomial coefficients. But yeah, so for this example, you have unordered sets, but repetitions are allowed. And in this example, you have unordered sets, but repetitions are not allowed. So you use this formula, which you'll notice is like very similar to this, except the top of the formula to determine the binomial coefficient is different. And that's only because you have to account for this number will be larger, thus the numerator is larger because repetitions are allowed, whereas this formula factors out any repetitions that would exist in the set, in a given set. One way to kind of easily calculate binomial coefficients, or you're not calculating them, is Pascal's triangle, which is a triangular array of binomial coefficients. So the rows denote the power of the of the coefficient formula. So x plus 1 to the 0 is 1. X plus 1 to the first power is x plus 1. So 1x plus 1, right? X plus 1 to the second power would be x squared plus 2x plus 1, as you can see. And you can do this all the way to the sixth power, to where you would have x to the sixth, 1x to the sixth plus 6x to the fifth plus 15x to the fourth, and so on. So yeah, this is a really helpful tool in general, but it's also a really helpful tool for combinatorics when you need to determine cases where you have unordered sets, and you have to deal with binomial coefficients. So I know that's a little bit confusing. I'm still a little bit confused about it myself, but I think everything will make a lot more sense once we actually start getting into probabilities themselves. And from what I've heard, these two here are kind of some of the most commonly used in probability. But it's necessary to cover these topics because they do come up, and when they come up, you're going to have to calculate them this way. So yeah, that's what I have for part 1 of my presentation on permutations, and this was on combinatorics. Next up will be a presentation on the basics of probability. So looking forward to presenting that soon. Thanks, guys. See ya.